This video is about transpositions, but don't worry, transpositions are something which you already know about. The definition is super simple. A transposition is a two-cycle, so in other words, a permutation of the form ij for some distinct numbers I and j. So as an example, the transpositions in the symmetric group S3 would be 1, 2, and 2, 3, and the other one would be 1, 3. So those are the transpositions in S3. What we're going to do in the last couple of videos about permutations are to investigate the importance of these transpositions. And really the importance is, as we're going to see, that every permutation can be written as a product of transpositions. And in fact, the ways in which you can do that give you interesting hidden information about the permutation. So to do this to begin with, we're going to prove a simple lemma about multiplying a transposition into a cycle of a particular form. And here it is. So lemma 2.14.1. The reason we didn't do it in video 14 is because video 14 was the one in which we did disjoint cycle decompositions, and I didn't give you the full formal proof, I just showed you why it was true. So for the actual proof, which you find in the notes, you actually need this lemma, and we need it now, so I'm going to put it in video 16 here. So what it claims is that if you've got some distinct numbers a0 up to am, then if you multiply the transposition a0, a1 into the m cycle a1 up to am, then the result is the m plus 1 cycle a0, a1, a2 up to am. So to prove this, let's just think what it's saying, right? This is an equality of two functions. If you want to show that two functions are the same, well, for sure these things have the same domain and codomain. The domain and the codomain are both equal just to the set 1, 2, 3, 4, 5 up to n, where n is whatever symmetric group we're thinking about. So what we have to do then is simply to show that they have the same value for every possible input. So we need to show that what? Well, let's give these things some names. Let's call this thing here S, this thing here T, and this thing here U. So S is the two cycle, the transposition, A0, A1. T is the M cycle, A1, A2, A3 up to AM. And U is the M plus 1 cycle, A0, A1 up to AM. And what we need to show is that for any number x, that S of T of x is equal to U of x. That's what it means for those two functions to be equal to one another, that they have the same value at every input x. But we can do this. This is nice and easy because we know how those functions are defined. So we just need to check all the possibilities. So there are some various different cases, and let's think about these case by case. So case 1, what happens when x is equal to a0? So then S of T of a0 is equal to, what does T do? Well, a0 up to am are all distinct numbers. So a0 is not equal to any of a1, a2 up to am. And that means T of a0 is just a0 again. So what I've got here is S of a0, which is a1. Okay, now let's try what U does to a0. U of a0 is equal to, U of a0 is a1 because U is the cycle a0, a1, a2 up to am. Okay, so for this particular value of x, S of T of x was equal to U of x, so we're happy in this case. So let's try the next case. So let's try x is equal to ai for some, well, I between 1 and n minus 1. Okay, we will work out S of T of ai. Well, T of ai in this case will be ai plus 1. Because I is less than m, so we're not going back to the start in t. Okay, and ai plus 1, well, I plus 1 is 2 or 3 or 4 up to m, so it's not a0 or a1. So what we've got here is just ai plus 1 again. And now let's work out what u does to ai. Again, I is something which is less than m, so we're not at the end of the cycle, we're not getting sent back to the start. So u of ai is just ai plus 1. And again, in this case, they agree. Okay, case 3. So what would happen if we were at the end of the cycle? So what happens if x is a m? Okay, s of t of a m is what? Well, t of am, if you look at t, am is at the end of the cycle there. So t sends am back to the start of the cycle. It sends it to a1. Okay, and s of a1 is a0. Now let's do u of am. And again, you can see that am is at the end of the cycle there. So u of am would be the thing at the start of the cycle, which was a0. And again, s of t of am was equal to u of am. All right, so there's only one thing left to check, one case left, and that is what happens if x is not any of the ai's. Well, in this case, all of the permutations, s and t and u, just send x to itself. Right? Remember the definition of a cycle. So the definition of the cycle u is that it sends a0 to a1, a1 to a2, and so on. Then it sends am back to a0, and any other number, it just leaves it alone. So in this case, s of t of x would be s of x. And that will be x again. And similarly, u of x is equal to x. Okay, so we've checked that in all possible cases, s of t of x is equal to u of x, and that means st is equal to u. So we've proved this claim. Okay, what can we get out of this then? I mean, why did we do this lemma? Why did I spend this time proving carefully that that lemma was true? Well, one of the reasons is that it helps to show this result I was talking about earlier, which is that every permutation is equal to a product of transpositions. And the reason is, let's look at the expression I've got on the top of the page here. So this is actually, it's not quite the lemma I wrote on the previous page. It's the same lemma, only with m minus 1 in place of m. But what we can do is we can use our result from the previous page multiple times. Because if you just leave a0, a1 alone, and then use the lemma on the cycle here, then it would tell you that this is equal to a1, a2 times a2, a3 up to am minus 1. Okay, and now we could do it again. We could leave this bit alone. We could leave the next bit alone, and we could apply the lemma from the last slide to this thing, and then that would say that it was equal to a2, a3 times a3, a4, and so on up to am minus 1. Okay, you see what I'm doing here? We can just keep going, and what you'd end up with at the end is that m cycle, a0, a1 up to am minus 1, is equal to a product of transpositions. It's a0, a1 times a1, a2 times all the way up to, the last one would be am minus 2, am minus 1. So we have expressed the m cycle, a0, a1 up to am minus 1, as a product of m minus 1 transpositions. So I'm actually going to write that down because it's important. A product of m minus 1 transpositions. So as an example, let's just take a concrete example of this up here. Like if you had the 3 cycle 1, 2, 3, then, for example, what we've just shown implies that that's the same as 1, 2 times 2, 3. And if you had a 4 cycle, I don't know, your favourite 4 cycle, 1, 5, 2, 7, then that is equal to 1, 5 times 5, 2 times 2, 7. So a 4 cycle can be written as a product of 3 transpositions. A 3 cycle can be written as a product of 2 transpositions, and so on. And best of all, it's just really easy for us to do this. So using that, we can now prove this theorem. The theorem says every permutation, not just cycles, every permutation is a product of transpositions. And we can prove this because we know that every permutation is equal to a product of disjoint cycles. So the proof is simply that every permutation, perm for short, is a product of cycles, and every cycle, as we've just seen, can be written as a product of transpositions. So to give you an example of how that would happen in general, like if you had a permutation which wasn't a cycle, like it might be 1, 2, 3, 4, 5, 6, 7, then to write that as a product of transpositions, we could just use what we've just done on the cycle 1, 2, 3 and use it again on the cycle 4, 5, 6, 7. So this will be 1, 2 times 2, 3, and that gives us the cycle 1, 2, 3, and then 4, 5, 5, 6, 6, 7, and that gives us the 4 cycle 4, 5, 6, 7.